So, welcome back, friends. We have been discussing topics related to unitary groups and representations. Along the way, we talked about the concept of representations of a group element, essentially how the unitary group can have representations in various vector spaces, essentially. And then we, to understand the concept of representations better, we made an analogy with quantum mechanics, essentially. So the analogy with quantum mechanics was that just like an operator has different representations in different vector spaces. So if the same abstract operator can have different representations in different vector spaces, okay, or different Hilbert spaces. Essentially, you take a one particular Hilbert space, the operator has one particular form. In another Hilbert space, the operator has a different form. Essentially, in the same way, the group element, which is can be thought of as an operator, has different representations in different vector spaces in the same way, in exactly the same way, essentially. Now this analogy is quantum mechanics is very nice, and along the way we learnt of two fundamental theorems, essentially. One is the Noether's theorem, okay, which I mentioned. We didn't learn about it in content, okay. So I'll just mention it because this is extremely important for us to know, essentially, these theorems. That what does Noether's theorem say? If we have any continuous symmetry transformation, there is always a conserved quantity. This is one of the most fundamental theorems of physics. This is there in classical mechanics. This can be imported into quantum mechanics, relativistic quantum mechanics, in everything, essentially. What does this say? Say, for example, that if you have space translations, then there is linear momentum which is conserved, essentially. Then if you have rotations in space, essentially, then there is angular momentum which is like a conserved quantity. And if you have time translations which are sort of conserved, essentially, the corresponding energy time translation which tells you that energy is always conserved. So relating symmetry with conserved quantities has been one of the major achievements of this, of Noether's theorem. Then there is this Wigner's theorem, which tells you that if you have a symmetry transformation on Hilbert space, it should necessarily be a unitary operator or anti-unitary operator on Hilbert space, essentially. So if we have a symmetry transformation on Hilbert space, it should always be unitary or anti-unitary, essentially. Now what we observed in nature is that most of the conserved quantities are essentially your physical observables. Most of the conserved quantities are your physical observables. There are some exceptions, essentially. Most of them are unitary operators also, essentially. So these are physical observables. So they correspond to conserved quantities, correspond to some symmetry operators, and these symmetry operators means that these physical observables are represented by unitary or anti-unitary operators on the Hilbert space, essentially. Okay, they are represented by unitary or anti-unitary operators on Hilbert space. Okay, so the entire point with this is that, so if we have physical observables, they are represented by anti-unitary and unitary operators. So the groups which we have thought of as unitary group elements can be thought of as physical observables in particular cases, essentially. They can be transformed into physical observables. This is a group of this is a transformations associated with a particular physical observable. What I meant was, essentially, the group of unitary operators corresponds to the symmetry transformations corresponding to a particular physical observables, like SU2 can be thought of as, I made this comment that it is generators of angular momentum. So that is what it means. Okay. So, behind that statement are these two powerful theorems saying that uh, Noether's theorem and Wigner's theorem, which tells you that SU2 is a generator of angular momentum. So, this statement which I made essentially that SU2 is a generator of angular momentum has something behind it, and that is how it is being substantiated essentially. Okay, that is how it is being substantiated. So, SU2 what? Okay. Now, there is one more thing with associated with SU2. SU2 is a double cover group. Technically, it's double cover group to SO3. Okay, so it's much more than being just isomorphic. So what it means that it is isomorphic to SU2. One of the, okay, it's more than that, but anyway it's isomorphic to SU2. But what it means that it is both 1 1 and on 2. So if there is a mapping between SU2 and SU3 SO3, or O3, you can find both 1 1 and onto mapping between SU2 group elements and SO3 group elements. So both 1 1 relation mapping so it is 1 1 and onto mapping essentially between SU2 elements and SO3 elements. So for every rotation in 3 dimensions on real vector spaces, there is a rotation, there is an element which rotates in complex SU2's 2 dimensional space essentially, 3 dimensional, so 2 dimensional complex. So there is an element for every, okay, for every 3 dimensional rotation in XYZ plane, essentially XYZ meaning as a real vector space essentially on R3, there is a rotation on C2. Okay, there is a rotation 1 to 1 correspondence to here essentially. So that means the SU2 essentially is like rotations. So there is a rotations in complex vector space and rotations in 3 dimensional can be considered as rotations in complex vector spaces. So SU2 can be considered as rotations in complex vector space. Of course, the representations are all on complex vector spaces, but in SO3 they are all on real vector spaces and everything essentially. So SU2 can be considered as rotations for complex vector spaces. This is important. Now there are other classes of one more point about representations, since we have been talking about representations a lot. The other point about representations is the representations can be both reducible or irreducible. This is also we learn in quantum mechanics. So what are reducible representations? Reducible representations, that means suppose if you have an operator O being represented on some complex some vector space essentially. So let me call it as psi. Now but psi has a form like essentially R or okay as a form which is like R1 of O 0 0 0. So it has some sort of O, okay, a block diagonal form of the matrix, such representations are called reducible representations. So this is in this vector space, of psi, essentially psi 1 and psi 2, psi 3, psi 3, psi n. So R has a form which is like block diagonal. So such representations, both psi and this, are called reducible representations. Okay. Now, if the psi doesn't have this form, or the operator doesn't have this form in the, so the representation, so let me call it R tilde, R tilde, R tilde. So this is R of theta, or meaning O, essentially this is O, R of O, should not confused with theta. Okay, so R of O, let me just by the problem, an operator A R of A, R of A, R of A. Now if this has this particular form, okay, R of A has this particular form on psi, okay, on this vector space, then your representation is reducible representation essentially. But instead, if R of A has a form which is all full, essentially, say R tilde of A, R tilde 1 1, R tilde 1 2, and everything, which is not block diagonal, then such representations are called irreducible representations. Which is actually these are the ones which were more interesting in physics, essentially the ones which are irreducible in physics, okay, and they are more interesting in most cases in physics, essentially, okay, they are more interesting essentially. Okay, we will see why, essentially what will form essentially about this particular thing. Okay, so now we have seen that there are these generators, and there are these operators, and there are these representations and everything. Essentially SU2 has a defining representation which is okay, which is okay, we will come back to SU2 now, essentially that you can have both. What we are interested is in constructing irreducible representations are interesting in physics because they can represent, okay, I can let the cat out of the bag. They can, why irreducible representations are interesting is because they form the physical states of a system, essentially physical states of the system are typically irreducible, okay. Irreducible representations. Okay. Now that we know essentially what are okay, let's now look at again come back to the vector space associated with the SU2. Essentially we will just see some more aspects about it, just look into it a little bit more before moving so to do with so okay. So one last prerequisite essentially, okay, we will see essentially, let us look at SU2 a little bit more detail with this all this knowledge essentially. Now SU2, if you remember, like in quantum mechanics, it is like the vector spin half vector space associated with spin half particles. So you can have 1 0 0 1 as your vectors. In this vector space essentially the defining representation or the representation of SU2 in complex is sigma x 0 1 1 0, sigma y 0 minus I 0, sigma z is equal to 1 0 0 minus 1. A little bit more detail about SU2. SU2 has real representations. It has no complex representations, it has only real representations, but there is no basis. So that means a representation of on a vector space psi and vector space psi star are equivalent. Okay, if you have a representation on psi and if you have a representation on psi star, both of them are equivalent for SU2. In SU2, but this is not true in general for SU2, SUN. For SUN, n greater than or equal greater than 2 not equal to, sorry, greater than 2. So for example, for n is equal to n is equal to 3 SUN, the representations are complex essentially. So the representations are complex. So SU3 has complex representations. Okay, so SU3 so okay. Now you ask the question, okay, you are saying, okay, you can ask me the question that, so you are saying SU2 has real representations, but you say that sigma x, sigma y and sigma z are a representation of SU2, they are generators of SU2. Then why is sigma y complex, meaning sigma y has so 0 minus I 0 essentially. You can ask the question that why is sigma y imaginary essentially, why is sigma y imaginary? The reason is there is no basis, and unfortunately in the case of SU2, though it has real representations, there is no basis in which you can show all the 3 generators to be real, In SU2 there is no basis in which one can show all 3 generators to be real. And that is the reason why they are called SU2 has pseudo real representations. SU2 has pseudo real representations. Okay. Now you can take another representation essentially of SU2. Now SU2 in 3 dimensions, you can take higher dimensional representation, but it is not SU3, it is still SU2. So the representations would be somewhat like this essentially. Okay. So they would be somewhat they will be in some form essentially of this particular case. Essentially you can take a vector space of this type 0 0 1 0 1 0 1 0 0. So in this case what happens is sigma x, sigma y, sigma z will be in a completely different form. There will be some form, actually one has to check and so on. So you can fill up this form essentially what this is sigma z as is. Okay. So okay. Check this out. So like I said, depending upon it is not SU2, this is just SU2. So SU2 representations higher dimensions you can always look at essentially. You can always have various representations like spin 1 representations of SU2. So you remember the spin 1 representations of SU2, that means so they are 3 dimensional essentially, they are 3 dimensional, but it is the still SU2 essentially. So these are various aspects about the group theory which we require. Okay. So these are the various aspects of group theory which we require. Now what has all this to do with Lorentz transformations and everything? Now I told you that what are what essentially I told you that there are this so just to summarize all the group theory which we have learnt essentially so far. So so what are groups? Essentially groups satisfy these conditions. So we started with the Dirac equation and then wrote down the solutions about this Dirac equation, and then we asked the question that what are these spinors, how do they transform under Lorentz group and everything, what are these things, what are these wave functions, and what has this to do? They seems to be coming out of from the energy momentum relation essentially. If you just assume to be that to be multiplying by arbitrary alpha and beta matrices essentially. So what are these spinors and what are these thing? Are they any physical or anything? Do they have any fundamental? Do these wave functions have any fundamental background to take them to be serious essentially? That is the basic idea. Now then I said okay, let us digress a little bit, and then I said that spinors are representations of Clifford algebra, or they are fundamental vectors in unitary groups essentially, and then we started discussing a little bit about group theory. So we said the group, so I did not connect why we need group theory, and I will let you know essentially group theory essentially why we need the connections between group theory. So the thing is that these are the group axioms: closure, associativity, identity, inverse. But for the present let us just take that this has something what is Clifford algebra, what is group theory and everything of unitary groups, what is it. So for that we needed to know a little bit about groups essentially. So groups we defined that they satisfy, these are sets which satisfy closure, associativity, identity and inverse, and they can be continuous or discrete. The continuous groups are essentially which are like rotational group. Essentially we looked into at length with the rotation groups. We looked at length with the rotation group, and we show that in rotation groups are represented by orthogonal matrices. So these are called rotations in n dimensions form, all possible rotations in n dimensions will form an ON group essentially, orthogonal group of n dimensions. And so we looked at in particular 2 and 3 of a rotation group. So in 2 dimensions it just becomes normal O2, one single rotation essentially, and this and this can be written in terms of a generator. Essentially, a generator of this cos theta and psi theta can be expanded 1 minus theta square by 2 and so on. So, and the linear term comes from sin theta. Essentially, if you just take, there are higher terms, expansion. If you do an expansion, there are higher terms essentially. So these are continuous modifications over unity. You start with unity and you do tiny infinitesimal rotations essentially, and the generators of such infinitesimal rotations can be defined by some x axis. And now what happens is, interestingly, if you have more than two dimensions, so you have 3 dimensions. So in the case of 3 dimensions, you have 3 parameters. We also told that how you can get this number of parameters associated with each group. Okay, if we have 3 parameters, and so there are 3 rotations in 3 dimensions, which is also understandable. And now this, the corresponding generators do not commute because they form because rotations do not commute in 3 dimensions. So correspondingly, the generators also do not commute, because a rotation in 3 dimensions will not go back to itself essentially, meaning if you interchange the rotation matrices essentially. Okay, and so we derived these generators in 3 dimensions and wrote them in this particular fashion. A generic rotation group element can be represented in terms of this generators, essentially in terms of these generators. Given these generators and their corresponding commutation relations is called something called the group algebra. The group algebra, and these groups are called in general Lie groups. These groups are called Lie groups essentially, meaning groups which are continuous, which are continuously deformed from unity to higher and higher elements essentially, and which satisfy algebra among the generators is called Lie algebra, and the groups associated with the Lie algebra are called the Lie groups essentially. And then we also mentioned the question about compactness. Essentially, the rotation groups become compact because their domain of the angles, the parameters is comes to itself essentially. 360 degrees is equal to 0 degrees. So Lie groups with such angles with domains for the angles are called compact Lie groups essentially. And I asked the question, this is where we are now for the first time trying to make the connection between all what we are talking about. We asked the question that there are any other non-compact groups, and we shouldn't call it a group in real sense, because I'll tell you in a few minutes essentially we will start looking at what is the use of, in the next lecture itself we'll start looking at what is the use of how they form a group. The boost will form a group. Boosts do not form a group of their own. In conjunction with rotations they form a group essentially. On their own they don't form a group. So Lorentz group, but can be represented like a cos hyperbolic and sine hyperbolic, such that, but these are non-compact. These are non-compact groups essentially, in the sense that the range of the boost is essentially minus infinity to plus infinity. But boost plus rotations form a group which is nothing but the Lorentz group, and we are going to come to the Lorentz transformations. But before doing the Lorentz transformations, we wanted to do unitary groups and representations. So we did the unitary groups. In the case of orthogonal, okay, so we did what is SU2 groups and the number of parameters with SU2 and SUN groups, and we derived that as SUN groups have n square minus 1, and special SUN groups have SUN in general UN groups have n square parameters, SUN group have n square minus 1 parameters. And then we started looking in detail with SU2 group, and the generators of this SU2 group are nothing but your Pauli matrices. And then we wrote down all this representations of the Pauli matrices, and we made an analogy with the representations. And then we said that how one particular case represents into in vector space represents in the operator, the same operator in different ways depending upon the vector space it works on essentially. Okay, then we looked at the SU2 group group and one dimensional, two dimensional fundamental representation, which is called fundamental representation. Then there is also something called the adjoint representation, which is a three dimensional representation, which is called the adjoint representation. We will talk about it a bit when we need it. Right now we don't need this adjoint. We will need it, but we will not need it currently. When we need it, we will come back to it. Essentially, what is the proper definition of adjoint representation? But this is like spin 1 particles, essentially spin 1 representation, and this is a 3-dimensional representation for SU2. So along the way we also passed about Wigner theorem and Noether's theorem, essentially. So now we will now okay, good. Now we are in a position to start discussion about the Lorentz group, so which we will start in the next lecture. Okay, I will stop here right now, essentially, and now I want you to digest all these concepts within yourself, essentially, and we will be using all these concepts to understand the Lorentz group, and from there we understand why the Dirac equation looks like that, essentially, why does it form like that, and what is its related, how the Dirac spinors transform under Lorentz transformations, and why do they transform in that particular fashion. Okay. So this background is needed to understand that particular aspect, essentially. Okay. So we will stop the background. I think we have covered most of the background required, but I want you to go through this background in more detail. There are a list of references given to you through which you can learn and go through them again to understand it, essentially. If needed, repeat these lectures a couple of times, and then I think you should be able to understand the background. With this, now we will try to understand the Lorentz group, essentially. Okay, I will stop here, and thank you very much. Thank you very much.